Welcome to Codex. Our speaker today is Darrin Speegle, who's a professor at St. Louis University. Darrin has made important contributions to wavelet theory, frame theory, Gabor analysis, and more. Today, he will tell us about simultaneous dilation and translation tilings of Rn. Take it away, Darrin.
All right, thank you. And thanks for inviting me to give a talk today. I'm really happy to be talking about this. This, as John mentioned, is simultaneous dilation and translation tilings of Rn. And this really represents the culmination of work over the last more than quarter century. So I've been working on this problem for more than 25 years, and I'm not sure there's much left to do. So I'm really excited to talk about this today because I think we finally understand what's going on here, and that's what I'm going to try to share with you. So let me start by just giving the definitions, what I'm talking about. So first of all, a measurable tiling of Rn is a collection of measurable subsets such that the intersection of any two distinct ones has measure 0, and the union is the whole space up to some set of measure 0. So just a regular tiling. And a wavelet set is very easy to define. So you have an invertible n by n matrix and a full rank lattice. So you won't lose much by just thinking of Zn here if you don't want to think about full rank lattices. But full rank lattices are discrete subsets, subspaces of Rn in a group sense. And then an A gamma wavelet set is a measurable set such that the dilations form a measurable tiling of Rn, as do the translations. So that's the object of study. We want to find matrices, lattices, and sets such that when I apply powers of the matrix, I get a measurable tiling of Rn. And when I translate the set around, I also get a measurable tiling of Rn. That's the object of study. I want to start with a few examples. So let's take n equals 1. We'll think about just R first, right? So here are two of them. So the first is if we just take dilation by 2 and translation by integers, then you can write down very easily a set that is a wavelet set. If you look at this set and think about it for a minute, you'll see dilations by 2. They definitely form a measurable tiling of R because the intersection of any two is at most, I guess, 2 points, right? Because if you dilate that out by a factor of 2, then they intersect at -1 and 1. So there is some intersection, but it's just a single point, which has measure 0. And if you union all the powers of 2 of the first set there, you get everything except for 0. So that's the union is R. Similarly, right, if you translate this to the left and right, you might get single point that intersects, but measure 0, and the union is again the real line. One of the things that I see there's something in chat. You'll let me know if
you're good. Go.
Okay, right, thanks. So one of the things that people thought about at the beginning was trying to find nice wavelet sets. So for example, for negative values, negative dilations, you can get a single interval that's a wavelet set. So I should have pointed out when I talked about the definition of a wavelet set, the definition is symmetric in A and A inverse. So anything that is an A wavelet set is also an A inverse wavelet set because we're taking all integer powers, and so it doesn't matter whether we take A or A inverse. So here we have for negative dilations, you can get a single interval. If you have a dilation of the form n plus 1 over n, then you can get 2 intervals, just like the first example above was when n was equal to 1. And for all other cases, you can get a 3 interval wavelet set. So these are kind of the simplest wavelet sets in R. They are ubiquitous, right? If you fix like A equals 2 and gamma equals Z, and you try to think, well, what does the collection of all wavelet sets look like? It's huge, right? So the collection, for example, the would generate the Borel sigma algebra if you took the sigma algebra generated by wavelet sets. It would generate at least that. So it's a big set of, there are a lot of wavelet sets, right? We're only writing down a few here, but there are a lot, and they're just everywhere in the line.
What is the reason for the name wavelet set? Why are they called like that?
Yeah, so it turns out that if you take the indicator function on a wavelet set and you consider that as a function in L2 of R, then the inverse Fourier transform of that is an orthogonal wavelet. So if you dilate it by the transpose of A and translate it by the dual lattice of gamma, then you'll get an orthogonal basis of L2 of Rn in that case. And that was the original motivation. I'll talk about that a little bit more once I've have some more examples, but that was the original motivation for studying them, is that they were the simplest example of orthogonal or orthonormal wavelets if you normalize them properly. And also for many pairs of matrices and lattices, they are the only example of orthonormal wavelets. So that was the original reason for studying them. Now that's kind of not really the reason I've studied them anymore. That's more of a secondary reason. The reason we continued studying them is more the geometry of the situation just got really interesting. That's why we're studying them now.
Thanks.
Sure. So here's an example in R2. The shaded set is a wavelet set. I'm not telling you what the dilation is, but it's you rotate by 45 degrees and then you expand by square root of 2. Right. So if you so the wavelet set in question means you take the unit square centered at 0, 0, so it has side length 1, centered at 0, 0, and you apply that matrix to that square. Then you set difference the applied matrix to the original square. That's the wavelet set I'm talking about. And here I've shown the dilation tiling on the left. You can see it just tiles it. And for the translation tiling, what I did was I just showed how you can translate the pieces to get a fundamental region for Z2. And once you can translate them to get a fundamental region for Z2, then when you translate them by all integer points, then you get tiling of the plane. So I haven't shown the full translation tiling here, I just shown how the pieces fit together to give you, like I said, this fundamental region for Z2. And this is one way of constructing wavelet sets, is by for determinate 2 integer matrices anyway, is to find these these square-like sets, and then you just apply the matrix, and then you do the set difference, and this will become a wavelet set under certain conditions. Right. So those are just some examples to kind of convince you that they exist. The examples that we think about now are much different than this. The ones we think about now, in general, we cannot prove that they have non-empty interior, for example. I mean, they're funky sets at this point, but this is the place to start here with sets like this, I think. Okay, so the question under consideration, right, is for which matrix lattice pairs does there exist a wavelet set? That's the question. It's easy to state. That's what has been keeping me busy for more than 25 years. Like I said, I started working on this in '95, and Martin and I announced on archive 21st of September a solution. So I hope you'll indulge me a little bit. I'm pretty excited about this, a problem I've been working on for more than 25 years. You can imagine that I'm excited to finally announce a solution. And this is the first time I've given a talk. I gave a talk in the faraway Fourier talks, but at that time, there was still a gap between we didn't have a full solution. And so I hope you'll indulge me. There's going to be a little bit more retrospection and kind of other things in this talk than there normally would be, just because I'm kind of just excited and eager to then kind of look back on the 25 years to see what has changed and what's happened. So the next slide is, this is from my thesis, right? So I'm just really convincing you that, so if you look 4 lines from the bottom, a natural question then would be to characterize all matrices for which there are wavelet sets, right? So this question appeared in my thesis in '97. That is stated a little bit differently than how I stated it today, but this is exactly the same question, right? This is this question appeared in my thesis, 1997, and Marshall and I have been working on this most recent paper for about 8 years, I would say, and I don't know how he feels. Maybe you can ask him, but I had completely given up on ever really finding the answer to this. It just seemed hopeless. But we did. So some things have changed since 1995. This is me when I first started working on wavelet sets, roughly. I know this was 1995 because this was right after I got married, and my wife and I only lived in this apartment for like 3 months. So I know exactly when that was. And I also remember this picture because I was really irritated for some reason that she was taking this picture. And looking at my eyes, I can't see it today, but I remember being really irritated for some reason. And in case any of you are worried that if you want to work on wavelet sets later and you're worried that working on wavelet sets will make you old, based on this, you might think that based on this, but I have evidence that it's not only people who worked on wavelet sets who got older. Here are the codex, the organizers, pictures of the organizers from 1995. So they too have changed considerably since 1995, perhaps more than I have, and they haven't been working on wavelet sets. So don't worry, if you want to work on wavelet sets, it does not necessarily make you older. There's probably something else that's causing this. I'll let you try to figure out which one is which. The one that says Emily is a bit of a giveaway, but other than that, I'll let you try to figure out which one is which. Okay. Anyway, no further ado. We're gonna do some more background. Okay. So if you're trying to attack this problem, I think the first thing you would be interested in maybe is forget about a set that does them both at the same time. Let's make sure we understand sets that do each one separately, right? I mean, you have to understand that first, probably, to be able to do the other thing. So I wouldn't have any idea who to attribute this to, but so certainly for a lattice, you can always find a set of finite measure that tiles. It's just a fundamental domain of the lattice. And the thing I want to point out is that every set that tiles by translations has finite measure and has the same finite measure, right? So that's kind of the thing I wanted to point out here. So that's the first comment, is that wavelet sets have to have finite measure, okay? So when can you have an invertible matrix that, for which invertible matrices do you have a set of finite measure that is a measurable tiling? And it turns out that's if and only if the determinant of A is not equal to 1. So the first condition is that if the determinant of A is equal to 1, then we cannot get a wavelet set. Okay, so that is the first observation. So from here on out, we're just going to assume the determinant is bigger than 1, because remember, it's symmetric with A and A inverse. So we can just assume the determinant of A is bigger than 1 rather than less than 1. Okay. Here's the theorem. Right, this is the condition. So if you have an invertible n by n matrix and a full rank lattice, there's a wavelet set if and only if this sum is infinity. Okay, so this condition, we had several conjectures, as you can imagine, over 25 years. We had no shortage of conjectures of what the condition might be. This one was never one of the ones we considered. at all. So what it's saying is that if you take you take a ball, normal Euclidean ball centered at the origin of radius 1, and you apply a matrix to it. All right, so A is your matrix. So I like to think of my matrix as having, let's see, I like to think of the inverse as having one eigenvalue that's big, and then two that are small. Like I think like an R3. So if you apply the negative powers of A, you're going to get an ellipse, like a really tall, skinny ellipse, right? So it's going to shrink in the outsides, and it's going to get really tall and skinny. And then you ask yourself, okay, how often does that intersect the lattice? Okay, so how often does it intersect the lattice? If it intersects the lattice too much, then you cannot get a wavelet set. If it misses the lattice enough, then you can get a wavelet set. That's what it's saying. So if these ellipses, if they miss the lattice enough, then you can get a wavelet set here. Okay. So that's the theorem. That's the characterization. So what I want to do, let me pause and see if there are questions on the.
Can I ask a question about this condition?
Sure.
It looks very interesting, and I'm wondering about two things. One is what happens if we change the ball to some other shape? Does it is it an equivalent condition, or it depends on the shape? And another one is, can we calculate it in concrete case? I mean, is this condition easy to check or difficult to check in a concrete situation?
Yeah. So the answer to your first question is it doesn't matter so much if you have a ball. I think you want to have a symmetric convex body that contains the origin. Yes, I think because yes, and the radius 1 doesn't matter either. You can take different radius. So as long as if you get a ball that contains your convex set and it is contained in it, then I think but I'm not sure if you get away with removing convexity or symmetric. I'm not 100% sure about that. But yeah, you can change it, and we do change it a lot. A lot of times we'll switch to cubes because they're just easier to calculate with. And the answer to your second question is I find it very challenging to compute. So it's not easy. We do have a couple of other conditions that are easier to check. That one, the sufficient condition for a wavelet set to exist is just the limit of these cardinalities is finite. Okay, so then the sum would definitely be infinity, and this is that's the sufficient condition that we normally actually check, and not this one. And then we have like a measure condition of a lattice subspace condition that I'll talk about later. That is the necessary condition for wavelet sets to exist. So we don't have a good handle on what this thing is doing at all in specific contexts. You give me a lattice, I know, okay, how about this? I know of examples of lattices that I don't know whether this is infinity or not. How about that? So yeah, so we don't have this. It's hard to compute, I would say, except in the cases where it's easy. Yeah. Yeah.
Okay, thank you.
Sure. Yeah. Oops, I didn't mean to do that. Anything else about that? I agree. It's a very strange condition, but we never would have. We conjectured many things to ourselves, and this was never any one of the ones that we conjectured. I mean, for sure. Okay. So I know you can see my cat. I just should say she's a rescue cat. She was like at a high kill shelter because she was like super aggressive. And she's really calmed down a lot, but I try not to move her around too much unless I really have to. So if it's not bothering you too much, I'm just gonna let her be. Okay, thanks. If it's okay, thank you. Okay. Let's see. So the next thing I wanted to do was to try and motivate this condition because I know it's weird, right? I kind of had three thoughts about what I could do. I could either ignore why that's the condition, which was pretty tempting to just say it and then ignore why it is. The second thing I could do was to, and I thought about doing this, to give you like an outline, which is a bunch of lemmas that you would need to understand, and then show you how to piece together the lemmas to get the theorem. And I thought about doing that. But I decided to do something maybe more ambitious. I have a picture in my head for why this is true, and I'm going to try to explain that picture to you. So I hope this, it's not easy. It's kind of, this is the heavy lift for the talk for sure. So the starting point is like, so if you take this matrix 2, 0, 0, 2/3 and the integer lattice, then there's not a wavelet set. That's because, right, think about, if we think back to our condition, so A inverse is, so this is getting these tall, skinny matrices, and we're expanding by 3/2 each time in the y direction. And since there is a lattice point on the y-axis, the number of lattice points is growing like 3/2 to the j, right? And so that sum is going to be summable, right? The reciprocal of that's 2/3 to the j. And so we get an infinite sum there, right? Because we're growing, it's growing up the y-axis at a rate of 3/2 to the j. That's how many lattice points we're getting, is 3/2 to the j. So 1 over that is summable. So there aren't any wavelet sets based on the previous theorem. But okay, but why really aren't there any wavelet sets? That's not a reason, that's just how you apply the theorem. So this is how I think about it. So let's start with our set. So it's just a slab kind of, what would you call this? So it's the interval 1, 2 cross R. So it's this big slab. And the key thing about this is that this, if I apply powers of A to this, this will tile the right half plane by dilations, right? Because the x's still tile, the y's just, they don't matter. So if I take a pretend wavelet set W, which we know doesn't exist, and we intersect it with these A to the j u's, then that has to satisfy two properties. It has to satisfy more than two properties, but it has to satisfy these two properties. If I translate those intersections with powers of A to the j u, then the translations have to be disjoint. That's because they are subsets of a wavelet set, right? If I translate the whole wavelet set, I get disjoint translations. So if I take a subset, then I also get disjoint translations, right? So this should be clear that we get disjoint translations, and I will say that these sets pack by translations. The second thing that has to be true, right? And now you see this, right? Already we have a sum being equal to infinity. So you think, aha, maybe, and you'd be right. This is the same sum that we're doing later. What also has to be true is that if I take the sum of the measures of A to the j, wj, that has to be infinity. The reason for that is it has to be, there's more than that, right? If I union the A to the j, wj's, I have to get all of u back, right? Because remember, W was supposed to be a wavelet set. The only powers of A that map W back into U are these. And since the union of A to the JW is all of R2, when I intersect it with U, it has to give me all of U. So this is telling me that these WJs have to have these two properties, right? This is weaker than being a wavelet set. This is just these two things. Okay. What happened there? So what we're going to do is show that no collection of sets can satisfy condition 1 and condition 2 and be contained in A to the negative j u's, right? So this is weaker than being a wavelet set. We're showing something like strictly stronger than we need to. So we're going to show you cannot have something that satisfies that packs by translations whose sum of these measures of these powers dilations are infinity, and that live in these strips. Okay, so we've got to do computations. I mean, we've got to. I mean, yeah. So the first thing to notice is that each one of these sets packs by translations, and so the measure can't be bigger than or equal to 1, right? We know the largest set that can pack by translations with integers is 1. Anything bigger than that, you're going to get overlap. So the measures of these have to be less than or equal to 1. So I compute the sum, right? So the only thing you need to know, right, I guess, is that the measure of a matrix applied to a set is just the determinant of that matrix times the measure of the set, right? That's what we're using for the first inequality. And then we just write down so this is finite, okay? So that's for j bigger than 0. For just j less than 0, we get a stronger condition on the wj's. We get the measure of the wj's is actually less than or equal to the negative j, rather than just being less than or equal to 1. So this is particular to the integer lattice. The first computation we made, whatever lattice we would have chosen, we would have gotten the measure of the w negative j's were less than or equal to some constant, and we would have gotten a finite sum. Here, this is specific to the integer lattice. So I have a picture, okay, that kind of got messed up. But so here's a to the negative 1u, right? And I'm imagining I have some w1 contained in there. So for each fiber here in x, what is the maximum height that w1 could have? Well, if it tiles by translations, then the height can only be 1, right? Otherwise, we're going to get intersection when we move up and down. So the height has to be less than or equal to 1. The width is a half, so the measure is a half. And that's true for each one of these slabs. We get the stronger estimate on the measure of wj. They have to be less than or equal to 2 to the negative j. And just magically, right, 2 to the negative j times 4/3 to the j is summable, right? That's what it boils down to. So this sum, this is again, this sum is finite, and so that's a contradiction, because in order we were trying to see right here if it satisfies 1 and the wj's are contained in a to the negative ju, then the sum has to be finite. So we cannot have infinite sum here. Okay, so I think you're starting to see maybe where you get the necessary and sufficient condition could be that some has to be equal to infinity, but it's still a long way. I think it would be too much. I don't see how you could possibly guess that condition would be from here. So I'm going to continue with the heavy lift for 2 more slides, and then we're done with the heavy lifting for today, and give you the idea, right? Let's change to a different lattice, right? And let's think, okay, how can I possibly construct these sets wj such that each wj packs by translations and the sum, when I dilate it back into u, is infinite now, okay? Now, again, this is weaker than being a wavelet set, so there's a lot of work to do. Once you show that this is possible, there's still a lot of work to do to show a wavelet set is possible, but okay, this is still the picture I have in my head that I'm trying to get across. So here's what we do. Okay, so the first thing is what I was saying before, right? For the positive dilates, there's nothing you can do. The measure of the wj's are bounded by some constant that depends on the lattice, and we're adding up the determinant of a to the negative j. We're assuming the determinant of a is bigger than 1. This is always going to be finite. The positive powers of j just don't matter, right? There's nothing, we don't care at all about the positive powers of a, I should say, right? They don't matter at all. We can never get anything from them. And you see that if you remember the condition, you see that we only looked at the negative powers of a, not the positive powers. So what's our idea? Well, so the idea seems again a little optimistic. We picked a Euclidean ball contained in U, so that, of course, a to the negative j of that ball is contained in a to the negative j of U, okay? And then we just thought, okay, what if we just took the largest possible subset of that we can that still packs, right? Let's just take the largest possible thing we can of that still packs. What would have to be true in order for that to be big enough that the sum of the measures back in U would be infinite. So that was our idea. We just took the largest possible Wj inside each of these negative dilates of the Euclidean ball. So what has to be true? Well, that's overwhelming when it shows up all at once, isn't it? Right. So Rj is the percentage of the negative dilate of the ball that we're able to include, right? So if Rj's are really close to 1, that means we've been able to include a lot of the ball inside our Wj. If you look at the sum of the measures of a to the j Wj, so we're mapping them back to U, right? The first step, that's just, okay, this is always true, it's the determinant of a to the j, measure of Wj. Then we substitute the measure of Wj for Rj, right? So in the end, we get that the sum of the maps of the a to the j Wj is just a constant times the sum of these Rj's. So we need the sum of the Rj's to be infinity in order for wavelet sets to exist, right? We need to be able to, the sum of the Rj's to be infinity. But, right, the Rj's you can approximate by the thing in the bottom, that is, so if that supremum is 1, so in the first inequality, if you take a set and you move it all around by translations, and if the sup of that is 1, then it packs by translations. If the sup is 2, that means you can break it into 2 distinct sets that pack by translations. If it's 3, you can break it into 3 sets that pack by translations. So this is saying that if I can break it into 3 sets that pack by translations, Rj is bigger than or equal to a third. I can, like, at least one of those subsets of a to the negative jb is going to have to be a third of the size. And then finally, it's a bit of a step maybe, but okay. It turns out that if you take a ball and you translate it around and you count the number of times they intersect, that is up to some constants. It's the same as counting the number of intersections in possibly a different ball, right? The number of times a different ball centered at the origin intersects the lattice. So since Rj is approximately bigger than or equal to this quantity, that's why we need that this sum has to be infinity. Okay. So like I say, that's the heavy lift. I knew it was ambitious to try and get this idea this picture I have in my mind across, but I wanted to try because the argument we have in the paper is very technical, and if anyone is ever going to think about reading it, I think maybe having this picture or this outline, I think it would be useful because this is how we got started, and this is how this is really the intuition behind a lot of what we did. So that's why I wanted to talk about it. Okay. So here's the theorem again, right? Just restating the theorem. Right, we have the sum of these cardinalities is infinity. Like I say, what we end up checking is not that the sum of 1 over these cardinalities is infinity. We usually end up checking that the limit for these cardinalities is finite, right? That is it implies that the sum is infinity, obviously. And so then a gamma wavelet sets exist. This is the condition that we end up checking, right? The first one, I don't know. That one's tricky. Okay, let's look at let's think about this condition. So it turns out that this quantity, if you look at powers of a matrix applied to a Euclidean ball intersect the lattice, that this has actually been studied quite a bit. Okay, this is a topic that has a pretty long history, and there are a lot of known results about understanding this cardinality. And this is the reason. One of the reasons we chose a Euclidean ball instead of some other shape is because when people study this, in the literature, they almost always are choosing a Euclidean ball. And so that's what we're doing too. We can use their results more easily. So of particular interest was when this goes to infinity, right? These are known as divergent trajectories. Normally they look at the powers of the matrix applied to the lattice intersected. They write it differently, but it's the same thing. So these, that's what they were interested in. So I want to show you a couple of applications of the theorem. So the first is we can recover this theorem. This was my very first theorem. It's my most cited paper, I guess. So if all eigenvalues are greater than 1, then there exists a wavelet set. So we can recover that based on the result that we just saw. So we can assume that gamma is the integer lattice. Then you might think that if all the eigenvalues are bigger than 1, and you take a -1 applied to the ball, it would automatically shrink it to be less than the ball. But that's not true, right? You can have like shear and stuff where it doesn't quite work, but it's almost true because you take a large enough power, then it will be contained inside the ball. And so that's what we're saying here, is that for a large enough power of j, then a to the -j of the ball is contained in the ball, which means the cardinality, if that intersected with gamma, is 1. And so the sum has to be infinite, right? The sum of 1, 1, 1, 1, 1 is infinity. Okay, so we can recreate this result of Larson and myself from 97. There is, Martin and I were able to improve on this. So if instead of all the eigenvalues being greater than 1, they're just greater than or equal to 1, right? It seems like a small change, right? But now we're saying, what if instead of just being bigger than 1, we're being strictly bigger than 1 in modulus, we allow some of them to be equal to 1 in modulus. Then turns out that wavelet sets still exist. And here's the proof, right? So what we do is you write A in real Jordan form so that A1 is expansive and A2 is, or in block form, right, where A1 is expansive and A2 has all eigenvalues 1 in modulus, okay? Then we construct this auxiliary matrix T that has the identity where the expansive part was, and the eigenvalue 1, the 1 in modulus stays the same, okay? And then we apply a theorem of Margulis from 71, who showed, this is known as Margulis' lemma, that exactly what we need, that the limit of this thing is finite, right? So this was the only theorem in this paper that he wrote, and it turns out to be the exact thing that we need to finish the proof, okay? So if it works for T, that's less than infinity, then of course it's also true for A, because A1 is expansive, so A1 inverse is contractive, right? And so that part's going to be smaller than just using the identity there. And so it's going to shrink that part as opposed to the identity. And so we get that if it's true for T, it's also true for A, right? And this, I think, also explains a little bit why it was 24 years in between the bigger than 1 and bigger than or equal to 1, is because somehow I think it's just necessary to know something similar to what Margulis proved to do this, to finish this. I think I don't think there's any other way. I think pretty much you have to know this in order to finish this. And people hadn't realized, it was just hard, right? It's a hard thing. And it kind of explains why it took so long in some sense. Okay. I thought there's, yeah. So the theorem is sharp in the sense that that's the largest set of matrices for which a gamma wavelet sets exist for all gamma, right? For every other matrix, I can find a lattice for which wavelet sets don't exist, right? So that's the largest collection of matrices for which you always can find wavelet sets. But Bovnik and Lemvig proved, and this is a really interesting result, that if the determinant of A is bigger than 1, but it also has one eigenvalue. Well, I guess this is true without that as well, but and it has one eigenvalue less than 1, then for almost every full length rank lattice, A gamma wavelet sets exist. So this has been known, I think, for 6 or 7 years. And so what Marsh and I were doing is like filling in the set of measure 0. We were like describing the set of measure 0 more precisely, is kind of how you can see this most recent theorem. So it turns out that when n equals 2, okay, things are very different. You really have to go to n equals 3 before you run into a lot of the difficulties that you run into. And that's because when n is equal to 2, a lot of things that are not equivalent when n is equal to 3 or higher turn out to be equivalent. So in particular, we have these 4 conditions, 3 conditions being equivalent to there being a wavelet set. Namely that if you look at the expanding direction for A inverse, that it does not intersect the lattice. That's equivalent to lim_inf being 1, which that was the condition that we've been using, that's similar to what we have for higher dimensions. And then we also have this this measure condition, right? I think let me not say too much about this, but this is just this is also now much easier to prove now that we know a lot of these results about these divergent trajectories, and we understand better how the negative dilates of A applied to a ball intersect with a lattice behave. We understand that a lot better now. And so this theorem, I understand it a lot better than I did 15 years ago. So I'll let you, maybe, yeah, I understand it a lot better. Okay, I'll stop there with that. So here's the theorem that is the easier necessary condition, right? So this is a necessary condition for a wavelet set. So what you do is you take a subset of your lattice, okay, and then you let V be the normal linear span of that. So it's a subspace of Rn. And then you intersect V with the negative dilates of A, okay? So if the limit of that measure is infinity, then there's no wavelet set, okay? So this is kind of like Minkowski's theorem. So this is saying that we have a symmetric body that is big, has large measure on some subspace. It has to have large intersection with the lattice, right? That's what Minkowski's theorem says essentially, and that's what we're using for this. Is that we're using Minkowski's first theorem that gives estimates on if you have how big your symmetric convex set is, you know how many lattice points it must intersect, right, at a minimum. And so that's what we use for this. Maybe I don't want to say anything more about that. This proof, it sounds really easy when I say it like that, but I think this may actually be the most complicated proof in the paper, is showing that this is actually necessary, gives a necessary condition. So this limit has to be finite for wavelet sets to exist, and that's the necessary condition I would check if I were trying to check a necessary condition. Okay, so I had some remarks about Minkowski's theorem, but I think maybe I will skip those for time. I said them verbally, so you heard them even if it's too fast. So I do want to give I have special thanks. I mean, you can imagine that when you work on something for 25 years, a lot of people help you along the way. And so I wanted to make sure I thanked a lot of people who, and I know I almost took this out because I'm afraid I'm forgetting somebody super important, and I apologize if I have. But the people that helped me a lot with this project, Marcin, obviously, my co-author, but I don't want to forget him. Dave Larson, he was the one who first introduced me to this problem. That was back in '94, I think, was when he first introduced me to the problem on wavelet sets. And he's always been very supportive of my career and of my research, and I appreciated it. Rick Lageson has a very strange connection. So I told Rick about this some examples where I have one eigenvalue bigger than one and some eigenvalues equal to one. So I had some examples like that I was showing him. And he said, yeah, okay, that's great. But, I'm writing this other paper and I really need an example where one eigenvalue is bigger than one and one eigenvalue is less than one. Right. So he really needed an example where eigenvalues are on both sides of one. And that gave me the nudge I needed to really sit down and try and focus on that. So thank you, Rick. Gu Qing, he was a fellow grad student at A&M. I haven't talked to him in years, but he was a great help in grad school working on problems like this. Barak Weiss was, he's the person who explained to us the relationship to like these old results and how we found like this result of Margulis and how we related it to, there's some old papers by Kenshin and that we use. And I emailed him and I said, hey, we have this necessary condition and this sufficient condition. We think they might be the same, And he says, oh yeah, well, it turns out that the thing I study is exactly when those two things are not the same. And so he was able to give us a lot of help. In particular, he told us they were not actually the same. Yeah, he really pushed us forward with his help, and he spent a lot of time on email just helping me and explaining very patiently what his work says and what he's done, and I really appreciate that. Eugene and Yang Wang, they did the characterization in 2 dimensions, which was huge. That made me realize that maybe there'd be characterizations in general. And then last but not least is Guido. He passed away recently. I don't know if, but when I first moved to St. Louis, Guido welcomed me to the WashU Wavelet seminar and introduced me to Marcin and Joma and Wojtek and many other people. And I wasn't a postdoc at WashU, but he treated me as if he was my postdoc mentor. And I owe Guido a lot. And I just wanted to, so I hope you'll indulge me. Don't mind indulging me. I'm feeling nostalgic after solving a problem I've worked on for more than 25 years. And I did want to thank some people who had really helped me. The preprints available on archive, and that's all I have. Thanks.
Thanks, Darrin. So invite you to smash the reaction button for Darrin here for a great talk. And if Dustin wants to end the recording,